Okay, this is our very last part. So this part is just another review on the actual atomic structure or the electron structure of the atom, I'm sorry. So how electrons are arranged and where they are. I know I kind of touched upon electron configuration briefly, but I realize you guys might need a refresher on how the orbitals actually fit around that nucleus. And I just want to add a couple more things in. So the current atomic model is called the quantum mechanical model. And that is all based down to Erwin Schrödinger, who used the wave-like and particle-like nature of the electron. He actually formed a very complex equation. The good news is you do not need to use that equation, but using that equation, he was able to map out the probable areas where you can find such electrons, and that is called quantum mechanics. So that's why his model of the atom is called the quantum mechanical model. Um, so I just kind of wanted to, I'm going to play this video and kind of talk about how electrons fit around the atom. And it might take a little bit to get going. Skip that part. So we're going to pretend the nucleus is in that middle part, all right? And so atoms have that nucleus in the middle. The very first orbital that every single atom has is the 1s orbital. And your s orbitals can fit 2 electrons. After your 1s orbital is filled comes your 2s orbital. And you'll notice that the 2s orbital is actually larger than the 1s orbital. That's because there are already 2 electrons in the 1s orbital, and your 2s orbital, those 2 electrons cannot fit exactly where the 1s electrons are. They have to fit outside of that area. And so you'll notice your 2s orbital is bigger than your 1s orbital. After your 2s orbitals are filled with their 2 electrons, you're going to have 3 different p orbitals coming in, and each of them hold 2 electrons. And these just show where the electrons can be. You'll see the red part. You'll notice the middle part is grayed out. But notice that grayed out part is where the 2s orbital is. So what it's showing you is that these are the regions where the electrons could be, the red parts. Usually, probably not in the middle because that's where your 2s orbital exists. Okay. And so your 3s orbital comes in. So the whole outer part of that 3s orbital is red. So we can't find electrons where the 2p, 2s, and 1s orbital fits. So your 3s electrons can only fit outside of that. And you can keep building up, and you see the orbitals get bigger and bigger just because those electrons that are being put into these new orbitals cannot exist where current electrons exist. I'm going to let it build up for a little bit. All right, and after your 3 different orbitals are each filled with their 2 electrons, then you would get the 4s orbital coming in. Okay, and those are going to fit 2 electrons. And that pattern is going to keep building. They're going to go on to d orbitals, but I'm going to stop there. Just because the AP does not focus that much on d orbitals. You have to be able to write some of them in configurations, but aside from that, they don't really test on like the looks. So let me skip that. And so here's a rundown of what the orbitals look like. This you definitely have to know. This you definitely have to know what they look like. Be familiar with these. If you are noticing these numbers, don't worry about these other quantum numbers. Just know your p orbitals kind of are in 3D space, so they kind of go in 3 different directions. These are your f orbitals. They look super crazy. Don't worry about the f orbitals at all. Okay, whoops, I skipped too much. So your s orbitals, again, as I said earlier, your s orbitals are going to get bigger as they go up, as we go further down the periodic table, because more electrons are going to fit, and they can't fit in the same space. And that's this right here. The radius of the sphere increases with the value of n. And what n means is it means energy level. Okay, so again, you have 7 periods on the periodic table, which equate to 7 energy levels. Okay, a little bit more information. So remember I said that the orbitals have to get bigger because the electrons cannot occupy the same amount of space. So here's our teeny tiny 1s orbital, and this is distance from the nucleus. The shaded part right here, this is likelihood of finding an electron. So if you notice, super big bump. So this is a very high likelihood of finding an electron so close to the nucleus. But when your 2s orbital comes in, you notice there's a node. Okay, that's a region where there's zero probability. Look at where the node is. It's at 1 angstrom from the nucleus. Look at the 1s orbital. That's where it's most likely you're going to find electrons. Right around where that 1 angstrom is. So what it's saying is where you're most likely to find an electron for the 1s orbital, you will not find a 2s orbital electron there. It's most likely going to be outside of the 1s orbital. When you get to your 3s orbital, you're going to see two nodes. This is where you're most likely to find the 1s electron. This is where you're most likely to find the 2s electrons, and your 3s electrons are most likely going to exist outside of that zone. Okay, you might find them there, but most likely they're going to be outside of the 1s and the 2s orbitals. Your p orbitals, those are your shapes for the p orbitals. Again, that node exists in between. This is that node again, and that is where your s orbitals are located. And so you're not going to find electrons there just because your s orbital electrons are hanging out right where the nucleus is. And same thing with your d orbitals. Those nodes exist because you've got electrons in that area. All right. So again, our periodic table order orbitals in order of increasing energy. So that just is for an element like, I'm going to pick copper is right here. We're going to start with the lowest energy orbitals. That's our 1s orbital. And then our next highest up is the 2s orbital. Then we move on to our 2p orbital. After our 2p orbitals, the next highest up in energy is our 3s orbitals. Then we go to our 3p orbitals. And then after our 3p orbital, the next highest up and energy-wise is our 4s orbitals. And then where copper sits is our 3d orbitals. Copper 1, 2, 3, 4, 5, 6, 7, 8. Oh, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks in. So that means every single orbital before must be filled. So you can just go in and fill these in right away. Okay. This one you might be wondering why F block is jammed in here. Usually our F block is removed and put underneath. Otherwise, if we jam this in here, notice how long the periodic table is, and it's removed for reasons to make everything fit on that periodic table. Okay. Taught me earlier saying that there are quantum numbers you don't need to know. These are the quantum numbers you need to know. So this first part A, that's this one. This is where that tells us the number of energy level or energy level that electron is on. Sometimes you hear the word electron shell as well. This is B. This is the letter denoting the type of orbital. Sometimes you'll hear the word subshells for orbital. And this one, C, this is the subscript that tells us how many electrons are in those orbitals. So with this electron configuration, you can tell how many electrons there are, what type of orbitals they exist in, and in which energy those electrons are found. So that is one thing you do need to be able to break down for an electron configuration. Last piece of information that I need you guys to know is there are some anomalies. So there are three elements that happen that sit inside the transition block that you need to know. I'm going to circle three right now. These are the three I've seen just because they're more common elements, silver, copper, and chromium. There's this one too, who's ever used molybdenum before. I can't even pronounce it. Okay, so these three elements do something unique. What they do is they promote a s electron into the d orbital. So this is the original configuration of copper. You'll set it from actual observed configuration. So what copper does is it takes one orbital and or kicks it to that d orbital. And why you do that is that it's actually to have full 2, 3s2, 3p6, and 3d. This is actually a more stable configuration, and what allows per 2 is to and repeat that 4s or s1 electron. For chromium, chromium will promote its 4s2 electron, one of them, to its 3d orbital. And so we'll actually end up with 4s1, 3d5. That's a half-filled d orbital, and that's actually also more preferred than a 3d4 or a d4. Okay, and that allows chromium later to ionize and get rid of the 4s1 electron. That, I believe, is it. That would be what you would need to know for electron configurations, and you need to know these unique cases. Okay? And if you have any questions, you can just ask. And I'm sorry, my dog barking in the background.